Okay, so this is the Centripetal Force experiment, and this is the way I rigged it up. Here's my fishing line, and we have the camera on a tripod, so for the filming later. So what I did here with the fishing line is I put it through one rubber stopper, pulled it around, put it through again, so this one is held in place, and then pulled it through the next one, and on the last one I made the knot. And then I put it through the pipe, and I made myself markers here at approximately 50 centimeters and approximately 100 centimeters. I will measure that in a moment. I want to avoid using the same radius data that you guys have, so I chose different numbers, and now I'm going to measure. So I'm going to put the first tape through here, so it's just beneath the pipe, and then I'm going to measure the radius. So I hold it like this here, so tape is right beneath the pipe, and my zero mark as far as the radius is concerned is at the center of mass where the rubber stoppers are, and I come up with 53 centimeters for one of the marks, and for the other one I'm going to come up with 106 centimeters. That one of them is double the other, that's just a coincidence. I put a couple of loops in here to hold on to the spring scale, and depending on how you hold the spring scale, if you hold it vertically or sideways and so on, the zero is just slightly different because the spring either pulls on it or not. In this case, I hold it upside down, so I still have to zero it here, and right now I got it at 0. Alright, now here comes the difficult part, the actual measuring. It would be really difficult if you did that totally on your own. Of course, I need somebody to hold the camera to film me, but he also needs to help me with the measurements. What I'm going to do is, as I'm going to start rotating, is I'm going to measure the average force that I need to exert in order to pull the rubber stoppers in to supply the centripetal force to the tension of the fishing line. Respectively, I measure the tension in the fishing line. Then, at the same time, I need to count the number of rotations, and Brandon, who is filming for me, has to keep track of the time, and I believe we said 30 seconds. Okay, so whenever it's convenient for me, that's when I'm going to start counting, and I'm going to give you a heads up when I do so. All right, here we go. Okay, it's not totally vertical, is it? It's not totally vertical. It's actually appreciably lower. What do you think, what angle that is? How much the angle is?
I'd say 30 degrees from perpendicular.
30 degrees from the, you mean from the horizontal?
From the horizontal.
Yeah, from the horizontal, 30 degrees from the horizontal. Because that actually changes the effective radius for the centripetal force, and of course it's gravity that's pulling the rubber stoppers down. As I'm turning this here, I can also already take my force measurement. I have to make sure that I just hold on to the casing. And my force measurement, it seems like an average of 3.5 newtons. Okay, now I'm going to give you a heads up for when I start the rotations, and I'm going to count down, okay? 3, 2, 1, start. .27 rotations, and I want to say actually I have an average force about 4.0 newtons. Okay, I'm going to stop this one. Okay, now I'm going to use the shorter radius. And, well, I already measured that to be 53 centimeters, so I don't need to do that again. Here we go. Measuring about 3.9 9 newtons. Okay, and again, I'm going to give you a heads up here. So 3, 2, 1, start. Okay, and I want to say about 4.0 newtons for this one as well. I should mention, we still keep filming here for a few more minutes. Actually, I should mention that I put all 5 rubber stoppers on there, and I bought them in such a way that they are close to 20 grams. They're actually 21 grams each, so I have a total of 105 grams on. Okay, now I need to go to the other masses, and I figure I'm going to do it this way. So I'm going to cut the last one off, and then thread it through the second last one. And I might have just cut it off in the wrong place. I don't have enough fishing line left. Oh, I see what I did. Okay. Still filming, right? And that's fine. Okay. Sure, we just left it like this. Finally got one knot. That's of course the problem with fishing line. Okay, so in that way, of course, I changed the radius. I made the line a little shorter. But of course, my center of mass also changed. Now it's between the third and the second rubber stopper, and my radius is 43 centimeters. I'm just going to take this one more measurement. Okay. Measuring about 3.3 newtons, but that may change once I start counting. Okay, I'm gonna give you a heads up again. So 3, 2, 1, start. And actually I'm at 3.9 newtons for this one. Okay. All right, and then of course in the upcoming recording I'll be evaluating my data. This one of course was 84 grams, and oh yeah, did you see by how many degrees it went down as I was rotating this one and the one before? What do you think? It's not as extreme as the first one was.
No, I'd say that was just over 10 degrees.
Just 10 degrees, this one, and I think the second one was probably also just 10 degrees.
About that.
Yeah, okay. All right. Thank you.
This is the Centripetal Force lab, and here's the analysis of the example data that I took and that you can view in the video that I posted. Okay, first of all, I'm going to look at these benchmark figures. It says in the data and analysis that these are benchmark figures for mass, length of the string, and time. and of course I have to use my own measurements. For the mass, I had at first 105 grams, another 105, and 84 grams. And for the length, I used 106 centimeters, 53 centimeters, and then I took some mass off. And because I used those rubber stoppers, that changed the center of mass, and because I also shortened the string somewhat, I only came up with 43 centimeters the third time around. For the time, we stuck with the 30 seconds. And notice that this is not 29 or 31 seconds, this is really 30 seconds, because we did measure to close the second, so it is two significant figures. Okay, these are the other data we took. We noticed that the entire assembly, the string and the rubber stoppers, were drooping, so we determined the angle, and in the video we estimated as 30 and 20 degrees. Since I took a video, I was able to remeasure that by stopping the video, and I came up with that we had overestimated the angle, and it's only 20, 20, and 10 degrees. On the forces, at first I measured a value as I was rotating it before I took the time and the rotation measurements. So I was whirling it around, and I said, hey, this is the force. And then I actually started measuring with the number of rotations, and as I was doing so, I apparently actually whirled it faster, and I came up with a larger force, which I had mentioned in the video. As I was done with each of these whirling it around, I said, oh, these are actually the forces that I measured, 4.0, 4.0, and 3.9. And then the number of rotations that I measured were 27 and 40, and that's also to the closest number of rotations, so it's not 39 rotations, it's really 40 rotations, also two significant figures, and 45 rotations. Okay, then for the essential force, the centripetal force in the horizontal, I have to multiply the measured force times the cosine, the measured tension force times the cosine of 20 degrees. So that's what I'm going to do here, 4.0 times cosine of 20 degrees. And before I do that, I'm going to check if I'm in the correct mode, and in fact I am in degrees, so that's going to give me the right answer, and that's going to be around at 3.8 newtons. Of course, these are same numbers, so came up also of 3.8 newtons. 3.9 times the cosine of 10 degrees, and that's also around at 3.8 newtons. That's a coincidence that for these three different assemblies, notice that the lengths are quite different and the masses are somewhat different and the rotations are somewhat different. Each time apparently I was able to measure the same horizontal tensional force. You could ask what happened to the remaining force here. Well, there's 3.8 newtons measured, determined in the horizontal, and that's a horizontal tension, so to say. The vertical tension is actually holding up the weight, and that should be about 1 newton here, because 105 grams, 0.105 kilograms is approximately 1 newton. And then, of course, which is, again is holding up the weight, the vertical tension. And of course, I don't add 3.8 and 1, but instead I would use a Pythagorean triangle, a right triangle, and that then 3.8 squared plus 1 squared. Take the square root of that, comes out to approximately 4.0. But we don't need to do that. I just wanted to mention that on the side. That's where the remaining tension force is. This one here is strictly in the horizontal. This one here was along the diagonal string. But the object strictly whirls in a horizontal direction, so that's why I had to calculate it the way I did it, and that's why I had to take this angle measurement here as well. Okay, let's get over here to the determining the speed with which it whirls, and speed is distance over time, and then the distance of a circle would be 2 pi times the radius, but the radius itself is, because it droops, is somewhat shorter. It's the length of the string times the cosine of the angle, so it's 2 pi times L over cosine theta, and for some reason I cannot highlight just that by itself, so in fact, so there it is. That here is nothing but 2 pi r, the circumference of a circle. Multiply that by the number of rotations, because it's the entire distance that the rubber stoppers went through, and divide that by the total time. So the entire distance divided by the total time, there it is again, that gives me the average velocity. So that's what I'm calculating with this one here, because these are the numbers that I measured. Okay, so I'm going to do 2 pi times 1.06 meters, already converting that from centimeters to meters, times cosine of 20 degrees, times the number of rotations, 27, and divide that by the total time, and I come up with 5.6 rounded. Looks like we have two significant figures here when we do the calculations. And then for the force, for the centripetal force that would be required to hold the rubber stoppers in, it's mass times velocity squared divided by r, but again the assembly is drooping, so it's v squared over L cosine theta, because this is the essential radius of the assembly. Okay, so again converting the mass to kilograms as well, so it's 105 grams is 0.105 kilograms times the velocity squared. I have the luxury here, I'm just gonna use second answer squared. If you don't have that on your calculator, you would type times 5.63 squared. That I divide by parentheses. The length L is 106 centimeters, respectively 1.06 meters, times cosine of 20 degrees. Close the parentheses again for the denominator, and hit enter, and I come up with a rounded 3.3 newtons, which is to be compared to my measured tension force of 3.8 newtons. So in the neighborhood, but of course some kind of measurement and experimental error is in here. Okay, the next one, I'm going to do the velocity first, of course. On my graphing calculator I have the luxury of hitting the second entry button a few times, and let's see, it's 0.53, shortens it up for me. Cosine 20 degrees, that's the same, and then the rotations are 40. There we go. Hit enter. I think I entered everything correctly, so I come up with a rounded 4.2 meters per second. That, let's see, I halved the essential radius. My number of rotations went up somewhat, and I come up with a slower velocity, so it actually, or slower speed, so it actually was rotating somewhat slower. And then again I'm going to do second entry twice, come up with the other equation. That's again 105 grams, again times the velocity squared. Again, here on the graphing calculator I can just say take that last answer and square that. Divide by 0.53. So if you use a different calculator, you may have to do it somewhat differently. But overall, you use the same equations, of course. I just have the luxury of doing it the way I do it here. Cosine 20 degrees is the same. Hit enter, and I come up with 3.7 newtons, which is pretty close to the measured tension force of 3.8 centimeters. Okay, second entry, and this time around I have 0.43 meters, and I have cosine 10 degrees, and this one is gonna be, let's see which number is that, our number of rotations, so that's 45 divided by 30, and I come up with 4.0. That one I would like to on the right as well. There we go. 4.0 meters per second. And here use this equation. So this one is going to be 4 grams, so 0.084 kilograms times the velocity squared divided by 0.43 meters is the length of the string now, and the angle is only 10 degrees. Enter, and I come up with a 3.2 newtons compared to a measured 3.8 newtons. So on all three here kind of measured and computed centripetal force, that it should be compared to the actual measured tension force. I have somewhat of an error in there. At this point I can't really decide if it's a systematic error. The reason I can't, it looks like a systematic error perhaps, but I can't decide if it really is, because I only have 3 measurements. That's just not enough measurements to make a decision like that. Anyway, that's how you analyze the data, plugging them into these equations, coming up with the tension force that you actually almost directly measured. Just the cosine of the angle has to go in there, and then the centripetal force that it would be needed to keep the rubber stoppers or whatever object you're using whirling around. Having it calculated here the way you saw it was a little bit lengthy. Anyway, this is the analysis for the data for the centripetal force lab.